Hey folks, so we're going to try to do some problems here associated with chapter 3 on energy. And by the way, if you hear any background noise, I'm doing this outside on the deck of my home, so you might hear some cicadas droning or some cars driving by. So please excuse that. I hope this is fine. I just thought I'd like to sit outside for a while. All right, so we have this problem. This is going to be one of the parallel problems at the end of chapter 3. And from group A, the ones with the solutions in the back of the book. And so problem 17. So we have this situation where a ball is dropped from a height of 9.8 feet. And now, of course, there's an airplane flying over. So we get some more background noise. And the question is, what is the velocity of the ball when it hits the ground? All right, so this is a conservation of energy problem. So what are we given here? Well, we're given that we have a height of 9.8 feet. And that means we're going to be dropping the ball 9.8 feet. And what's unknown is the velocity when it hits the ground after having dropped 9.8 feet. So what are the equations we're going to use here? Well, so the first thing we need to realize is that we've got conservation of energy. And remember, basically what that means is that the total energy remains constant throughout the process and is equal to the kinetic energy, represented by the letter T, as I mentioned in the video, plus the potential energy, represented by the letter V. So the sum of the kinetic and potential will always be the same. Now, at the height of 9.8 feet, we have a situation where the kinetic energy is zero. The ball is just stationary at that point. So the energy at that height is the potential energy. So what we need to know is the potential energy. And for gravitational potential, remember, potential energy is the energy of interaction. And so this is gravitational energy that we have. So we're going to have mass times the gravitational acceleration constant, 9.8 meters per second squared, times the height, and that's the potential energy. The kinetic energy equation is 1/2 mv squared. Now, here's the thing. The total energy is going to be equal to the potential energy at 9.8 feet. When the ball hits the ground, the kinetic energy, all the potential energy will have been converted to kinetic energy. And so if we calculate the potential energy at the height of 9.8 feet, then the kinetic energy is going to be equal to that. And that's going to require that we solve for v squared. So I'm going to go through this and set it up, and then of course we're going to slip into our friend Wolfram alpha. So let's go ahead and figure this out. So first thing is, what's our potential energy? All right, so here's the thing that's kind of strange. We don't know the mass of the ball. It's not given to us. So what the heck? How are we going to do that? Well, the thing here is to realize that the kinetic energy at the ground level is equal to the potential energy at 9.8 feet. So that means that we're going to have, at 9.8 feet, we're going to have a certain potential energy, and that's going to be equal to the kinetic energy at the ground when the potential energy is equal to zero, and that's going to equal 1/2 mv squared, which is, and again, point this out, this is the final velocity when it hits the ground. And again, just to reiterate, we have the situation at the ground level, the potential energy is equal to zero, and that means that the ground kinetic energy is equal to the total energy. All right. So what we're asking here is not for the kinetic energy of the ground, we're asking for the velocity of the ground. So let's solve for that, okay? So if we just rearrange, so let me rewrite this down here so it's a little bit more straightforward. This is where we get to have a little bit of fun with algebra. And what we're going to note here, if we're solving for v, all right, then I'm going to divide both sides by m. And you'll notice that what happens here is that the m's conveniently disappear. So we don't need to know the mass of the particle here. So what we've got is g times h, and again, this is at 9.8 feet, so I'm just going to go ahead and write this in. That we have our gravitational acceleration times 9.8 feet is equal to 1/2 v squared. You just heard that squeaking sound. That was my dog walking through the door, deciding that it was too hot to be outside, so let's go inside. I'm staying outside for a little bit until we finish this problem. So again, we're trying to solve for our final velocity here, so we're going to rearrange things a little bit. I'm going to multiply both sides by 2. So that gets rid of the 1/2 on this side. So now I've got 2 times g times 9.8 feet is equal to v squared. All right, we having fun yet? I bet we are. All right, and so now I need to solve for v again. So the v squared is going to be, we just need to take the square root of both sides. And so I'm going to just rearrange things a little bit just to my liking. I take the square root of both sides. And so I've got 2 times g times 9.8 feet for my velocity. Now again, there's unit conversion here. I'm not going to be worried about that unit conversion thing because we can again use Wolfram alpha to help us out with that. Because g is going to be, you remember that our gravitational acceleration is equal to 9.8 meters per second squared, and feet and meters we need to convert one or the other. All right, so let's move on to Wolfram alpha. So I'm going to pause here for a second so we can move to Wolfram alpha. Okay, so here we are in Wolfram alpha, and you can see what I've done in my entry bars. I typed in the square root of 2 times 9.8 feet times the acceleration due to gravity of 9.8 meters per second squared. And this time I decided to go ahead and type that in rather than, as you remember from past examples, you could just type gravitational acceleration, but it's actually, I thought, easier to just type in the number at this point. So we've got it. So you can see that what we get here in this is a result of 7.652 meters per second. All right, so there's our result. That's the speed at which the object hits the ground, 9.652 meters per second. Do you want to see what that is in miles per hour? Here it is, 17.117 miles per hour, in case you're interested. So remember, Wolfram will do all those unit conversions for you. So let's go ahead and go back to our particular velocity here. And so we've got our speed as, and again, 7.652 meters per second squared. Okay, so you can see I've entered the formula for velocity, square root of 2 times 9.8 feet times 9.8 meters per second squared. And what we get is our calculation of Wolfram alpha, which does our unit conversion for us. It's 7.652 meters per second. If you're interested, of course, that Wolfram also calculates things like miles per hour, etc., and other units, but 7.652 meters per second is our speed that we've calculated. I'm just going to round it off to 7.7 meters per second is the speed of the object. And you'll notice that the mass doesn't matter. The speed is the same regardless of the mass. So it doesn't matter if I'm dropping a bowling ball or I'm dropping a tennis ball. The speed when it reaches the ground will be the same, ideally. Now, of course, we all know there's things like air resistance and stuff like that that complicates matters. But in this situation, those differences are going to be relatively small, particularly from falling from a height of just 9.8 feet. So that's how we would calculate the speed. So there you have it. This is how we calculate the speed of an object dropped from a particular height, recognizing that the potential energy at the top is converted to kinetic energy at the bottom, all due to conservation of energy. Ask questions if you've got them.